All right, just a few things to go over in this section. We mentioned this earlier in the lab we did a couple weeks back, that tension and what that is. We haven't really defined it yet. So this is a name for a force that a rope or a string or a chain exerts on a hanging object. And not even always a hanging object, anything that you're pulling with a rope also exerts tension as well. So it can be a string, it can be a rope, or anything like that. Just not a spring, nothing that's bouncy or elastic. Because that would be other forces as well as tension in that case. So if you have something hanging from a ceiling, you have the force of gravity pulling this object downward. And so you have the force that the weight exerts on the rope. So it's a force that this bottom part is pulling on the top part. So the bottom part of the string is pulling on the top part of the string. So the force of the bottom part of the string is pulling on the top part of the string. And then vice versa. The top part of the string is pulling upward on the bottom part of the string. So you have the force of the top pulling upward on the bottom part. And if the string is not moving, if it's not breaking, if it's not pulling the weight upward, if it's staying in place, then we know these are balanced forces. And the forces must be equal to each other. So the force of the top on the bottom must be equal to the force of the bottom string on the top string. So everywhere within the rope, tension has to be the same. Because again, if the rope's not moving, then the forces have to be balanced throughout the rope. So force is constant throughout the rope. As long as the rope is not moving, that's true. Y'all have this side down? Okay. Now, if instead you pull down with a force of, let's say, 50 newtons, and the rope only could pull upward with a force of, let's say, 30 newtons, in that case, you have unbalanced forces and the string breaks. Because now you have more force being pulled down, the rope can't exert the same force upward, and that's why ropes and strings break. So if you do pull on something and it stays unbroken, then it's exerting the same force back on you. So I can pull with the force of, say, 2 newtons, it pulls back with 2 newtons. I can pull the force of, say, 10 newtons, it's still pulling back the same force if it's not broken. But if I pull really hard and it breaks, I've exerted more force than the rope can pull back on me, and they're unbalanced forces in that case. Do you have this down now? Very good. Okay. Now, if instead you're pulling upward with a force of, say, 50, and the rope only pulls downward with a force of, say, 30, then the rope's going to bounce upward. And that would be a case when you have acceleration upward and the rope is bouncing upward and not staying still. Let's say in a tug of war, you have two people pulling on either side. So one person on this side is pulling with a force at 50 newtons to the left. On this side, they're pulling with a force of the same exact force, but to the right. We know that this string won't go anywhere because they're balanced forces. Now, how much tension is in the rope, though? Is the tension 100 newtons? Is it 50? Is it 0? Think back to what you did yesterday in experiment. You did something really similar to this. What did you see in your experiment? Based on that, what do you think this would be? Yeah, exactly 50. So the tension in the rope would be 50, not 100. And that might be surprising. You might think, well, why don't they add together? Or why isn't it 0? Don't they cancel out each other? Well, the rope's not moving, right? If they're pulling the same force, it's not going to move at all. So it's the same as if you were to just have a rope attached to a wall. So let's just say that you're pulling the rope backward with a force of 50 newtons. But there's no person on the other side moving the rope backward. What is the tension in the rope? Well, it's also 50 newtons. So in this case, if you pull with the force this way to the left 50 newtons, the rope must pull back with the same force against the wall. So in both situations, whether you have two people pulling on the rope or a wall holding the rope still, it's always 50 newtons of tension. So whatever force you pull forward with, the rope will match backward in the other direction. Okay, in your book, I'm going to go through an example problem on page 104. Actually, I'm sorry, not 104, on page 106. So they give you a 50 kilogram bucket being pulled up by a rope. The rope will not break if the tension is 525 newtons or less. The bucket starts at rest and is lifted upward at 3 meters. It is moving at a constant acceleration of 3 meters per second. If the acceleration is constant, is the rope in danger of breaking? So there's a lot going on in this problem. Let's go through this step by step. So we have a 50 kilogram weight being pulled upward. And it starts at rest. So initial velocity is 0. We know it's displaced 3 meters upward. Acceleration is constant. So we know that it's a number. We don't know what it is, though. So it's not 0. It's constant acceleration. We're not given the number for that. We know that tension can be up to 525 newtons. Before it breaks. What we want to know, though, is how much tension does it actually experience? So we need to find the force that the rope experiences. Force equals mass times acceleration. We know the mass is 50 kilograms. We don't know the acceleration, though. So without the acceleration, we can't find the force. So we have two unknowns. We have force and acceleration as unknown. So we need to find the acceleration to solve for the force. So what we can do is go back to a problem that we had really earlier, I think it was chapter 2 or 3, where we used an equation for velocity. So we know initial velocity is 0 meters per second. We know displacement. We want to find acceleration. Are we given anything else in the problem? I thought we were given, yeah, we're given also final velocity. They tell you in the problem that the final velocity of the bucket is 3 meters per second. So if we know final velocity, displacement, initial velocity, we can solve for acceleration. You remember the equation we can use that has all those variables in it? Okay, so final velocity equals initial velocity, both squared, plus 2 times acceleration times displacement. We can solve for acceleration. Final velocity, 3 meters per second. Initial velocity is 0. Displacement is 3. And now we can solve for A. So we can get rid of this, that's just 0. 2 times 3, get 6 times A. 3 squared. Okay, so now we have 9 equals 6 times A. And we can solve for acceleration. So we do 9 divided by 6. For sig figs, we have 2 for both of these. So we have to report to 2 significant figures. For that, what do we get for that? 1.5. So acceleration equals 1.5. So now we know acceleration. What we want to know really is the force that the rope experiences, which now we can figure out. So we know the mass is 50. We know acceleration is 1.5. We can multiply m times a to get the force. Okay, so 50 times 1.5, 75. So that's the force that the bucket, or that the bucket exerts. So that's one force in play. Now let's think about all the forces though in play. So we have a downward force that gravity exerts and an upward force, tension. So those two together equal the net force. So we have a net force of 75 newtons, which we found from the equation. That net force, though, would equal the summation of these two forces. Tension is upward, that's positive. Force of gravity downward, it's negative. So what we found is a net force. What we need to find the individual forces, the force of gravity and the tension. Yes. Well, unless you're like thinking like a tug of war when it's on the side. But generally, if it's a suspended object in the air, we would say that tension is upward and gravity is downward. Okay, so are you with me so far in this equation right here? So we used m times a, the acceleration of the bucket, which was 1.5 meters per second. The mass of the bucket, 50 kilograms. Multiplying those together gives you the net force. We have the net force, which would equal the two forces in play. Added together, we have tension, positive, force of gravity, negative. So that's the equation that we're using to solve for the individual forces acting on the bucket, force of gravity and tension. Okay, so what's the force of gravity? Well, that's just the weight. So the force of gravity would equal the mass, which is 50 kilograms, times 9.8. So whenever we are given the mass of an object, multiplied by 9.8, you get the weight, you get the force of gravity. So 50 times 9.8, what is that, 490? So that's the weight of the bucket. That goes in for FG. We can now solve for T. Add 490 to both sides. We can solve for T. And that equals 565. So the tension is 565. So does the rope break? Well, it says in the problem it can withstand a tension of how many newtons? Yeah. Right. So would it break? Yeah. So the rope would break in this case because the tension is more than it can stand. Any questions about that? Okay. On page 106 and 107, work on all those questions. So do 32 up to 38 on those two pages.